A disclaimer. So, unfortunately, I have only half an hour, and there is no way I can go through my exercises on time. So, what I decided is to invent a new technique called copy-paste live coding. So, I have exercises and I have solutions, and rather than watching me typing, I'm gonna just copy-paste the solution and like walk through that and comment on that. So what happened to be the most popular recursion data structure? Can you guess which one? So we're gonna talk about list, and let's start with a function. Let's calculate multiplication of all elements in a list. And the way you can do that, you can start with a naive solution, which is using for each. And actually, I'm quite happy that I'm going to just copy that, because I haven't written anything with var for ages. In fact, I've never written anything with var. This is the answer. So, and since it's a recursive data structure, we can actually use a recursion to solve this problem, right? What we do, we just match on the structure, and in case it's nil, we return just 1, and in case it's a list, we multiply the head of the list with the result of that recursion. Does it make sense for you so far? It's like really simple example. Then, of course, we can use something from the standard library instead of writing that ourselves, right? So there is product, but let's assume that we are not having that function. We don't have this. That would be too easy, right? So, and I want you to think about how to write that with fold right. Any recommendations on how to implement this? One, and then cool. So this is one function which is popular, and I assume that you were more or less comfortable using it. So, but there is another one which I want to talk about. It's yeah, we want to solve this problem called range to generate the list of integers, starting with the given and going to 1. So again, we can start that with a loop. And this is the ugliest code ever, I'm telling you. Anyway, what we do, we just prepend a variable at the beginning of the list, and then incrementing the variable, and so on until we go to the number. So let's run it. Yay, that's what we want. Then the same thing, again, we want to, since it's a recursive data structure, what we want to do is to go from one integer to the list. So here, the important thing is that at the previous example, we were going from the list to a number. Here, we're going from a number to a list. So, yes, this is a very simple recursive solution. What's wrong with it? Yes, and in Scala 2.13 we have now this function called unfold. Has anyone used it so far? Yeah, only 2 people, so 3. Oh, or not that many. But it does the same thing as this recursion in this example. So what we can do, we can just write effectively the same code. So we start with a number, with the seed, and then we pass the function what to do on the next step. Here we just return a pair, an option of pair with the current recursion step and what's going to be on the next step. Does it make sense? So these two functions, fold right and unfold, apparently, if you think about their generalization form or more abstract version of these functions, where we get rid of this list, where we get rid of integer, that's going to be our two well-known functions from recursion scheme theory called kata and ana. And what we're going to do, we're going to go through the exercises and build an understanding why such a simple functions can be generalized and how they can be generalized to this kata and ana and why these functions are useful. So we're just gonna copy this signature of the fold right method and try to implement that. Again, starting with naive solution. Usually in functional programming, you can solve problems by staring at the signature of a function. Just because there are only few things, the only implementation of the function based on the signature you can guess. Okay, I have initial value, I have z, and I have operation, and I need to return a. Maybe I can return z, which is a, but then this function would be constant, right? This would compile. So instead of doing that, what else we can do? We can pattern match on initial value on list. Then if it's nil, we can return the seed value. Otherwise, we can call recursively ourselves, right? So let's take a look at the solution. Oh, 1 second. So that's exactly what I said. We pattern match on initial value, then return z or call ourselves. But there are problems with this solution. It's not really well optimized. We pass around this z and op several times, right? So we can improve that by introducing a new function, a new nested function. So instead of passing them around, we will have that nested function, then recursively call it with a new list, with the tail of the initial list, and then just use the provided variables from the top level. But the part with the matching will be the same. So basically that's what we do. Oh no. How do I do that? I'm glad I'm not actually typing these things because, yeah, sorry about that. Maybe I should type actually. Anyway, or maybe you can go like that. Why I'm not doing that this way? Anyway, so again, the idea is simple. We just don't pass the things around. But we don't have to actually have this kernel innate value as a value. What we actually can do, we can just return this function instead of like starting calculation right away, right? Let's make it a little bit lazy. And that's not exactly needed, but we are trying to change things so that at the end it would make more sense. Yes, I'm just like trying to create a solution which would fit our goals. That's why we are passing list as a return value, we return function. But that's absolutely the same as before. Then, instead of doing this nested function, we can just return the anonymous function. And I know that not that many people are familiar with this syntax, and sometimes it's confusing, but eventually that's what we want to do. We want to return a function from list to A, and we will have this kernel here so that we could call it recursively. Does it make sense for you? Are you following me? So the idea is simple. It just, instead of having a value, like having a named function, just return an anonymous thing. So that's a solution for fold right. And unfold actually is quite the same. And we're not going to talk about like all of the steps that unfold has. Instead, we just open the solution, and I'll show you that basically it's the same thing. Again, we have this recursion call here, but the difference between fold right and unfold is that here we destructure our data structure at the on the left side of our pattern match, right? And here, what we do, we at the end of our computation, we grab the things together, so we create a data structure. Same thing as on my first example, we were going from a list to a seed value. Here, from a seed value to a list. So basically, we're going to go from B to list of elements and return the same, not the same, but dual function. So to show duality better, we need to change a little bit the signature of fold right. As you can see right now, fold right has, no, this is not true, this one. So yeah, here, fold right has two parameters, z and op. It's an initial value and operation function. And unfold has only one parameter, function f. So to show duality, what we want to do, we want to combine these two parameters together. And let's see how it goes. First, z, instead of having a constant, you can change that to a function from unit to a value a. Effectively, it's the same, right? So you just change that to z calling a function, to calling a function. Then, if you think about how to combine these two functions, they since they have the same return value, they can be combined in one. So you can have either unit value or a pair of element and of E and A, which is in Scala programming language either unit or E and A. So since either unit do not make a lot of sense, we can replace that with option. So at the end, what we've got is option from E and A to A. That's also called a pattern functor, and we will talk about it a little bit later. But that's how you can think about, like, how do I understand what recursion does? Like, how do I understand how to get this pattern functor? And the idea is simple. On the left side of this pair, you get a value which will be the result of the entire computation. On the right side is the value that is you're going to have through your recursion on each. So what do you do on each step? If it's the end step, then the left side. If it's the require next computation and recursion, is the right side. So yeah, let's talk about how to get rid, how to factor out the data structure from fold right. Right now, it's tightly coupled with list because we have pattern matching. We know that the structure is list. We know that it has a nil value, it has head and tail, and let's think about what we can do about that. So the first thing is to understand that which parts are corresponding to which. So pattern match on list is that part of the, so I removed the part that are not related to this. Then recursion is this calling kernel. This is the second step. So as you can see, the first thing we're doing here is destructing the structure. Then we call kernel. Then we call computation. So as I showed here. So 3 simple steps. And we can actually implement them. Like we can have 3 functions and we can think about their signatures and we can think about their implementation. So that way the apply function will not have anything to do with the list, with the data structure. It would just know that there is 3 operations that we want to call in a certain order, and that's it. So the first thing is to provide signatures. So the step 1 is going from a list because that's the only parameter that we have. And why is it we have answers already here? Interesting. Anyway, and that's all we know actually on the first step. We know about list. Then we don't know anything yet about the second step. Let me do it backwards. And we know that this third step, since it's our operation, we know exactly the signature of the operation. It goes from option to A, right? So here we can just replace that. Then second step should be like this, because that's what step 3 can eat, option of the pair ENA. Because we said that we can pattern match on list, we know already that it can be option of E and list E. So it's either head and tail or nothing. So that's how we build our way to understanding the signatures of these 3 functions. So as I said, the step 3 is just our operation. The step 2 and 3 is just the step 1 and 2 is just calling a recursively kernel and destructing that. So here, if we look at this function, it's just a combination of 3 things: step 3, step 2, and step 1. And there is nothing in apply which correspond to list. Oh. Yeah, they return the same value, but you probably figured that without. So we do the same destructuring. We can do the same destructuring for unfold, where the steps would be backwards. First, we do computation. Second, we do recursion. And third, we doing structuring or embedding into data structure. So what's interesting, there are a lot of different terms for the same things in recursion schemes. Based on which library you use, you can think about different things like bases, embedding, and projection. And for me, at first, it was counterintuitive that they call the operation where I create a data structure embedding, because I was like, even more, the operation where we're destructuring something called projection, because projection for me is creating a list, but in fact is just a projection of the next step. If you were looking at the tree downstreams, that's what projection means. And this is the language we use at Drosti library, Scala library for recursion schemes. Anyway, unfold, I'm not going to talk about the unfold steps, but they're absolutely, idea is absolutely the same. I'm actually encourage you to copy this. I have that up on the GitHub, and I encourage you to do these exercises because I worked on them so that the steps would be super minimal. Like, and maybe it's not a great setup for this talk. I understand that in half an hour we just need to run through that, and maybe it's a little bit confusing, but still, if you go and try to do that manually, then it's better to go step by step than jumping around, because recursion schemes are not obvious, but they are simple. So anyway, yes, this is unfold, same thing. We're building our understanding of what signatures are, and then just copy their implementation from the previous thing, like step 1, or it's just F, and so on. So at some point you must understand that copying options through this typing option several times is not convenient. So you want to introduce some type aliases, and that's what you do. You just grab these two things. Since we want to get rid of this list of data structure, we can just call it S, and then replace that with any recursion data structure. Here it's pattern functor. As I said before, we're going to talk about this a little bit more, but here is just a higher kind of type in which we have just one parameter, because the other one comes from the data structure. And what we want to replace all occurrences of the list with S, and all occurrences of option with FS. And as you can see, the signatures of methods become really simple. It's just S to FS, FS to FA, FA to A. Does FS and F to FA remind you about anything? Exactly. So why not use functor from, say, cats? So here I just read an implicit from functor option composed with a pair, and I use kind projector for the simplicity. But the idea is simple. I need a type which can map over the option of pair. And then the step 2 becomes just fmap over fmap over kernel, which is quite simple, right? Look at this. The step 3 is our function, which is given to us. The step 2 is fmap over some functor. It doesn't have to be list at this point, so we got rid of our data structure. And the third step is going from S to FS2. And if we factor it out from our function, then our apply becomes data structure free. That's basically what we do. We introduce a new type, list f of option f. This is the same thing, but outside of our function. So fold right is now super simple, but and when we have this top level type, then we introduce a new functor, same as before, but we use list f now instead of option. So the same f that we had on the previous slide. Then I decided not to copy that actually, so that we could go faster. And then we have this project list function, which goes from list, and here we have concrete types. So our fold right now is f. Actually, you call project on your data structure, then map over kernel, so it's recursive call, and then apply your computation. And that's basically a very, very abstract code. So the same thing goes for unfold. At the end, what we have is functor, data structure, and value a, and we go from the value which we calculate on that initial given type, then do a recursive call, and then embedding that into the data structure, like in range. What we did there, we first calculated the next value, then we mapped over the recursive call, and then we embedded that, we created a list. We started to combine 10 plus 9 plus, I mean not plus, but creating data structure. So apparently these two functions are generic kata and ana. So fold right is called kata, and it goes from so it's the idea is that when you try to do that recursion, it can be the idea is that the fold right is the concrete but very useful for the list. And in fact, even if you generalize it, you still can use that as a fold right. Does it make sense? I hope it does. Yeah, and computation is staying the same. Like you can provide everything. Then if we're going to talk more about the okay, we don't have time. Anyway, let's take a look at the final example, I guess. So since it's function, you can compose them. You can compose the kata and ana, and that's gonna be a hylomorphism. So it's just a composition. And here I have a few examples of how to use hylomorphism. The canonical one is factorial. So you use both the product function and the range function. The second one that I really wanted to talk about was quicksort and divide and conquer algorithms. In fact, divide and conquer algorithms are often can be easily represented as hilo, because the kata is conqueror, and so you can go from the value to the structure, and divide is another one. So here, if you want to ever be super cool at funk interview and write whiteboard crazy implementation of quicksort, you can show that you know Hala, and this is the entire thing. So anyway, guys, this is the talk that requires a lot of questions. I expect you to ask questions. Maybe we don't have time right now because it took me too long to figure out how to copy, not copy, and so on and so forth. But please come. I'm here till the end of the day, at least till 5 a.m. You can ask me questions, because this is a fascinating topic. Thank you.